Hi. In this episode, I'm going to talk to Vlad, who is a researcher in quantum systems and quantum computing. He's a practitioner building software systems around quantum computing. And I'm super excited to have him and talk to me and also share his wisdom and knowledge on this episode of podcast. See you there.
Thank you for joining me on this podcast today. It has been a long time coming. I met you at the Agile Myths Architecture Conference last year in Berlin. I had a short chat, and I think that was enough for me to be curious about what you are doing and the type of problems you're solving and your journey. And I think I'm glad that we were able to make some time to come together and have this conversation today. So thank you again for coming in. And I hope you have a good experience talking to me and sharing your insights, wisdom to our audience.
Thank you, Vivek. Yes, it is indeed a pleasure to join the podcast. It doesn't happen often for me, so I'm actually quite excited to see where we are going with this discussion.
Amazing. So, right off the bat, I think it'll be great for Vlad, for yourself to give a quick introduction about yourself. Let maybe have our audience know about your story and what I would love to also know about what is your journey overall, what brought you to what you're doing today, and then we get into the meat of our conversation.
Yes, sure. So, uh, I am currently working as a postdoc researcher at University of Jyväskylä in Finland, and my research interest and area of activity nowadays is quantum software, so quantum computing, but it is more into the software things and how the quantum computers get integrated into the larger computing infrastructure and how you interact with from the classical world into quantum and yeah, this is like in a nutshell. We will go deeper into that. So before I have started my career at Nokia back when Nokia was the king of the hill of the mobile phones. So it was about 2001. And it was like the dawn of the smartphones. So it was an interesting journey. I stayed there for about 7, 8 years. Uh, and then I moved to Nokia research. I think I was always like attracted by this not very immediate problem, so something that has a longer horizon. And at Nokia Research, I have been working with like web APIs when they were in their infancy. Still remember now, like how impressed I was by Leonard Richardson RESTful web APIs and what you can do to build up networked systems. And then, yeah, had also a short foray into uh, augmented reality and mixed reality applications. Also at Nokia, this was around 2012, and then I moved back into like closer to production. And this was at the time when Nokia sold their devices and services to Microsoft and wanted to reinvent. And we had one attempt to enter medical software, and there I was exposed to regulations and how this affects software, uh, these software intensive businesses or activities. And from there, I got this interest into how to develop quality software and keep it regulatory compliant, and what are the frictions between like a regulatory specialist and software specialist, and how to address this kind of tensions. After Nokia, I have been so I had an attempt at this to live in the startup world. So started Compliance Pal, and the intent there was to make this regulatory ops, so reg ops for medical software, and after that I moved into academia. So University of Helsinki, the market was not quite ready for that kind of level of automation in the medical or medical device world. And yeah, I have been working in a project in about RegOps at Helsinki University, and after that, I don't know how to say it, but maybe this latest interest in quantum software was maybe accidental. So a former colleague and my told me like, look, we are building up a quantum software research group in Jyväskylä. Like, why don't you join, and let's see where this goes. And yeah, it happened. So almost 1 year ago, and it has been quite an adventure to go into a very new topic, very deep tech, but I would say that is on the verge of breaking out of the lab, and at some point in the near future, hopefully, we will see some real life activity related to this. I hope that this is like enough intro. We haven't, we left some space to discuss things in detail.
Amazing, Vlad. That is such a broad range of experience in the ecosystem. I am firstly very curious about your Nokia journey. I think especially in its heyday, there was so much of regard and almost celebration of the Nokia ecosystem. I think before iPhone and Android, all that came in to take the prize, I think Nokia dominated the world. And I'm interested to hear a little bit about, if you could share, what was your experience at Nokia, especially around its heyday before, smartphones and web-enabled devices became the cool thing. How was it like being at Nokia at that time for you?
Well, when I started, or my role was mostly in enabling IP over cellular networks. So, and the operators and the mobile industry, they have kind of a different idea than, let's say, the future thought about it differently. And yeah, it was more closed, more controlled. I don't think that I could have imagined back in that time that you would have all the opportunities that you have today. So you either had to be in a really large company and be part of this large industry consortia like 3GPP, IETF, and yeah, I think that in a way it is understandable because they were building enabling technology, but they were quite good at that. But I think that in a way they were like that kind of organizations, they were unprepared for the open world that web was, and what you could build without asking anyone's opinion or permission and things like this. And in a way, I think that the mindset was there, and like it is quite sad, and I'm still like going back talking with ex-colleagues about what it could have been and where we are today. But I think that everyone learned some lessons there, and yeah, here
Yeah, I
we
can't
are.
imagine any single person who hadn't had a chance to experience the Nokia phones at that time. Um, I also want to get your thoughts on the effect of Nokia on the ecosystem in Finland, especially I think at one point of time it was the highest talent density in amount of innovation work, and the work around enabling devices for people to use. So it'll be great for me and also the people tuning into this podcast to learn how do you see that impact post Nokia on that ecosystem, especially in Finland.
Yeah, I think that the impact is long lasting. So even if Nokia is still around, so it's still one of the major network equipment manufacturers, providers, uh, but is a completely different company. And I think that they were, so from the heyday to where we are now, there have been, so the collapse was gradual. So the transition collapse, yeah, but it reinvented themselves. So it's like they are still around. So that's like a positive. Uh, so every kind of wave of downsizing has like uh, caused like one round of startups, and uh, this kind of like entrepreneurial spirit, and um, yeah, even if they were, you could see it as a mobile phone. I think that, or this kind of device business. I think that there were people that were looking at other things inside the mothership there, and yeah, I think that there are examples of companies that have done quite well, and they you could say that they have heritage. Their heritage is in Nokia, and uh, it is quite. I think that even now, like looking back, it is quite a something amazing that for a country that is relatively small, so it's like 5 million people in Finland, you have one company that was like the center of the universe for a while, and it allowed people to think big, and yeah. So this was something that uh, you can still see today, and I think that like if you look around, you find people that used to work in Nokia in current companies, and so on. So is like the impact is still present. Yeah.
All right. Okay, I want to now go to the core areas that actually caught my interest and also our conversation for today. You mentioned that getting into quantum computing and building for quantum systems came as an accident for you, like an accidental uh, participation. I would love to learn a little bit about how was that as an accident and how was your experience getting into this whole domain. Before we talk about the moving pieces of the entire paradigm, it will be great for your story to be around, like how did you get into that, what was the accident about, and how did you really take on this completely brand new area of computing.
Yeah, well, what can I say is, so my knowledge of the field was somehow limited, and yeah, I'm following like what is in on blogs, like some scientific articles, but it was quite shallow, the understanding. But talking with my contact there, so he described like how. The whole like the field from a software perspective is very immature. Uh, uh, is led by, or understandably, by scientists, physicists, algorithm developers. So they use software as a tool to implement or to achieve or perform experiments to assist them, but they are not exposed at all to let's say the rigor that you need in real life to take it to take some technology, especially software, to take it to a larger audience. And I think that this was the trigger. And my background being like, okay, I have seen friction between software engineers and regulatory specialists, which typically they are like former engineers, not necessarily software engineers. So this was like a motivation to try to improve that and bring some I don't know, insight or something like and I think that it was like a bet for me. I wanted something that is new, a bit different than what I have done before. And what I discovered afterwards is that it's like all software is software in the end. Doesn't really matter like where it comes, like what is like quantum has its particularities, medical software has its particularities, like industrial has other, but in the end it's just a variation of some well-known patterns, and they need to be applied. And that was like all the background was in my background was quite a match for this domain. And I think that after 1 year we start to see some results in our group.
Amazing. All right, I think we are at probably right time to start maybe giving a picture of what this is all about. So if you have to probably explain to someone who may be living under a rock for the last few years, and they might have seen quantum and they read about quanta and maybe in pop science, how would you explain especially the field around quantum computing to them, assuming that they have some understanding of general computing, the John von Neumann systems?
Oh yeah. So that's something that is a bit of a shock, like when you get into this quantum computing. So although so first of all, like quantum computers are leveraging the principles of quantum mechanics, and those have been discovered probably, I think, if I'm not wrong, end of 18th century. So that was the theoretical part. Quantum information technology in some rough form, I think that it was 1940s, at some time that then the first actual algorithm that would use that, Shor algorithm emerged in 1994. So we see that although it is like a long field, depending where you are starting from, is quite new. And the actual, like the last developments or actual developments happened in the last 7 years or so. So quite new and very fast evolving field. And one thing to notice is that quantum technology is much larger than quantum computing. So there are other applications are quantum sensing, which is also very new, quantum communications. So this kind of like communications that are resistant to eavesdropping. So those are other fields in which quantum technology is used, but quantum computing is more in the same category as like like traditional computing. So you have a device, you want to program, you want to achieve something with that. And this is like, yeah, in a nutshell, the history. So what makes it different comparing to other like to the traditional computer? You mentioned von Neumann. Is that so? In the traditional computing, we are using bits to transmit information, and the bits can be either 1 or 0. And in the quantum world, we have qubits, which are they can be in many states at the same time. So you could imagine like a qubit is like a sphere, a sphere, and then the values, like the qubit can be anywhere on the surface of the sphere. So you could describe the state of the qubit using the amplitude, so the angle from the horizontal plane, and then the phase, how it moves into the vertical plane. And that's like quite let's say a departure from traditional computing, because how to deal with this kind of like in fact, you don't have a value. It is like a distribution of probabilities. But those are not really, like a qubit like that is not that useful in practice. So you need to apply some properties that are unique to quantum mechanics. So one is like superposition. So you apply some pulses, or so you control the qubit to be in two states at the same time. So you could see it as 0 or 1 with a probability distribution of 50-50. The other important thing about the quantum computing, or the other property, is the entanglement, in which you link the state of two qubits so that the end result is that you have like a 0-0 or 1-1 with the same probability distribution. So 50-50. And these are, so besides this, there are also transformations, so in X, Y, and Z axis, and these are the basic primitives to build quantum circuits. So this is how quantum program look like. So you have a number of qubits. You apply the transformation called called gates, and then you have a circuit, and then you measure the state, and the state collapses into classic bits, so the one that you measure, and basically this is your solution, or this is how you run a program. One thing to mention here is that when you measure, the state is lost. So it is like a one-time event. You cannot go back. You cannot, and because of this, you also cannot debug quantum programs in the same way you debug classical programs. So there is no like step function or step in, step out. These don't exist. So this is like in a nutshell how like quantum computing is different. And then because you have these differences between, so in the classical world we have bits and other like more complicated data structures, and in the quantum world we have qubits. So there is a challenge at this point, because very few people know how to map like the problems of the real world, which are expressed in classic data types, to quantum world where you have qubits. Yeah, like that would be the way. And these qubits can be like, nowadays we have in the range of like tens, but in the future when we have like proper quantum computers, they can be like millions. So how do you program these things? But you may wonder, like, what is the advantage? Like, why do we do it then? Yeah, like if they are so different, and what we have. So because the quantum computers can, so they don't have to go iteratively like classical computers to explore solutions. So they can do everything simultaneously. So you handle the whole solution space at the same time, and then you find, by measuring, you find what is the solution. So they have computation power that is not available or not feasible with classical alternatives. So this opens some. So mathematically, so quantum computers implement. So they are or all of them that I'm aware, they use they implement some sort of algebra, so Hamiltonians. And if a problem is appropriate for that kind of mathematical model, then your quantum computer will perform very good. So, but say it another way, quantum computers are very good at non-polynomial problems, so optimizations. So this can be traveling salesman, logistics, chemistry, and pharma, like molecule folding, and obviously, like, this is everywhere in the press. We have cryptography, and because the first, like, practical quantum algorithm was for factorization of prime numbers. Yeah, so, or factorization, so finding prime numbers. So that's like the, let's say, the holy grail of quantum computer. So it will kind of like render useless all encryption algorithms that we have nowadays. So a very scary, how to say, outcome.
Amazing. Let's maybe dig deep into some of the facets that you mentioned. And I think I will want to start first by really thinking about, as a consumer or a builder around these computing systems, you described some of the use cases where a quantum computer is magnitudes of powerful than compared to me a traditional computer. And if I look at, like, let's imagine I'm a programmer and I want to be able to see a difference between writing a program using classical approaches on a classical computing or digital computing, and then seeing the improvements of the same logic, the same program that I'm trying to solve for on a quantum computing. What could be that use case? Like, is there a specific scenario or use case where you feel that if I run it on a traditional and then I build it around a quantum, I would see massive differences, and that would be the first big wow moment for me as a programmer?
Well, it is not possible nowadays, but I think that the prime example is the Shor algorithm, so factorization, which gives you exponential advantage over classical computing. So this is something that is very hard to achieve by other algorithms, and so it is. Although initially I think I thought, like, when joining this area, that quantum computers will give you exponential or like advantage in any kind of field, is not the reality is a bit different. And this is also because in theory everybody works with ideal qubits which don't have errors. They behave as you want, but those don't exist in practice. So quantum computers nowadays are very rare. So you can use them if you are part of a research organization, or if you have commercially you have to pay for them. So all major cloud providers, they allow you, they have quantum offerings or services for quantum computers, but they are very expensive, and you need to know what you do in order to start using them. So you could start making or running quantum programs in simulators, but the number of so you can do it on your laptop. I think that based on our experience, you could get pretty an interactive experience for up to 20-25 qubits. Then the computing power needed to run experiments increases exponential. So every new qubit doubles the computational resources, and I don't have the latest numbers, but the largest simulators are around, or simulations performed on supercomputers are around 50 qubits. So if we think about Shor to break internet encryption, for that one you need millions of qubits. So we are very, very far away from that. But yeah, I mean, this is where we are. Regardless of this, I think that the state nowadays is that we are still in this kind of foundational phase. So everybody from the whole stack, from the actual qubits, so middleware, software, applications, we are learning what to do and how to do, or how to take advantage of these ones. And because of the current limitations of running this kind of Shor class algorithm, I think that the first kind of, in my view, the first real use of quantum technology will be in optimizations. I have seen, we work with one bank that is doing price estimations based on different, I think that the price was related to some housing. So housing price estimations for loans or something like this. And their experience is that it kind of works. It requires high expertise. So they have some mathematicians and physicists that work on this. They understand both the problem and the mathematics to be able to create these programs. But their findings is that they can achieve the same results with classical computers right now. So quantum computing is not yet ready for prime time. So everybody is in the lab mode now. So small improvements, some are like bigger improvements, but is more. So at the bottom layer, the physicists are trying to control the matter, to build more accurate qubits, so the fidelity there, and then in the upper layers, so we have other problems. But I have to say that what was a bit surprising for me was that the software stack, is quite, on the upper layers, is quite mature, and it borrows quite a lot from the classical computing.
Amazing. What would be the hello world of a quantum computer, right? So if I'm approaching a new language, a new paradigm, and I want to just write something and build something which seems like a hello world for that, what would be that for quantum computer?
Well, depends on the skill of let's say the practitioner. Yeah. So I think that in my demos, because I'm more into the software aspect, so I want to demonstrate how the software, the pipeline works, like from the classic to quantum and back, and how you get the responses. So mine is a very simple program with 2 qubits. One is like a Hadamard gate, which is puts the qubit in superposition, and and then there is another gate for is called C0 for entanglement. And in a way, so this is like the simplest quantum program that you could build. So it has 2 qubits, but they connect, so they have also a link between them, and that is something that is not possible with the classic computing, because there is no entanglement and superposition there, and that would be let's say for a software engineer, that would be enough, because that will allow you to write the program. And typically you write the program using a toolkit like Qiskit. So this is coming from IBM Quantum, and the user or the way to use it is so the programming language is Python, and the quantum part is like a DSL that allow you to perform the quantum to apply the quantum gates. Google has another framework is called Cirq, and then there are others that are they are mixed, like general purpose, but also machine learning, like PennyLane. So this is from Xanadu. Microsoft has Q#, so it is a C# kind of language that allow you to write programs here. So they are all open source. The Qiskit is like pip install Qiskit and you are ready to go. Yeah. So the threshold is quite low, and also the usability of this. So this is like the software engineer. Yeah. Like you are more interested into the mechanics of the software. Yeah. Well, if you would be an algorithm developer, your hello world will be a bit more complicated, and it would be like a benchmark on, let's call it like quantum Fourier transform, QFT, and that will allow you to do. That would be like the hello world for you, like the baseline, yeah, in which you get something, and quantum Fourier transformation is the building block of Shor, so it will be enough. Like that's a good baseline for an algorithm developer or a physicist. So yeah, depends who you ask, but in even for algorithms, Qiskit has a library of algorithms. They are already implemented, so you don't have to go to implement Shor or Grover. Or any of the well-known algorithms. So there are even hybrid algorithms that are, I think that they are useful also for machine learning. So they are in the optimization area. So machine learning, traveling salesman, and this kind of things. Yeah.
Interesting. Vlad, you had mentioned some time back around the challenges of converting and mapping real world use case to this world of qubits and qubits manipulation, either through superposition, entanglement, and transformation. I'm curious to learn a bit on what do you see as the challenges of translating a real world scenario and a problem into qubit? Like maybe take example of uh, the traveling salesman problem. I think we have been always taught like traditional computing, it's a non-polynomial problem, and one aspect is to really take, okay, what do you want to do with the traveling salesman problem, convert into a data structure and write an algorithm that kind of figures out the shortest number of steps that a traveling salesman can cover a particular area. And I think as a programmer and algorithm developer, my challenge is, what's the right data structure to capture the state, and what's the right algorithm that can solve in a kind of a realistic time frame. What are those similar challenges when you have to start mapping these real world scenarios to a quantum computing paradigm, according to you?
Uh, well, I can go back to that. So I think traveling salesman is one like standard example, but and um, maybe it's better, or I have a better answer if I go back to this banking example, because I have actually they have explained it to me. I'm not I'm not an algorithm like guy. Yeah, like I'm more into software orchestration, running OPSI kind of things and patterns. And so the challenge that how they explain it to me and I understood is that, so the inputs, the number of inputs, like when you analyze like the trustworthy of somebody that asks a loan are like huge. Yeah, like you could determine many, or they keep track of many and they model many. But the problem would be that you have, so how many you could, or which are the ones that are important to map into the qubits? And this is like, how do you reduce them? And then the output will be like, what do you measure in this quantum circuit? And the way they model this is that you have a very big matrix, and that like parts of it goes into the qubits. And how do you do handle that? And I think that this is because it is a very so we don't have like practical experience or success scenarios, because this is how engineering is typically done. Yeah, like there aren't early adopters in the field. Yeah, so we have some let's say theoretical results for some algorithms that require millions of qubits or large number of qubits, and then we have the nowadays reality where you have like hundreds maximum. Yeah, like for some computers there are, but they are special ones, they have maybe 5,000 qubits. So how do you map these large numbers of like your features into this smaller set? And this is like this is something that is uh, not is not easy to handle. So it requires a deep understanding of the field. So what is the problem? It requires some mathematics that are, I think that they are beyond the, let's say, the mastery of normal developers. Or the yeah, like mainstream developers, they don't deal with that. So including myself, so that kind of mathematics I have done it at university. If you are going into these radio systems where you need to handle all kind of like Fourier transformations and matrices, and that you would use it, but or in machine learning nowadays or AI, but that is also like very deep. So you don't have this kind of like groups of people, or so first of all you don't have groups of people like this, and then the second will be like you don't have one person that masters it. Yeah, it's even rare. So these are problems that you face when adopting this technology.
Interesting. So you basically are saying that one is definitely around number of variables that you have to consider as part of solving any kind of a problem, but also some of the concepts required to express that could be little bit above the mathematical knowledge that most programmers have. Like, frankly, after I left my university, I never have to apply, um, you know, basic calculus also in my day-to-day programming. I never have to
Yes.
do that. So I think there's a very limited set of people who kind of have a strong mathematic base and they keep using that also in their programming jobs. And I think that's what you're referring to is it's a niche skill and that
Yes.
is also not mainstream just yet.
Yeah, it is not yet. And I think that also this is because it's so new, yeah. And we have seen it in other domains. Like machine learning would be one, yeah, where 10 like 15 years ago it was called big data, yeah, like the problems were like into data ingestion and preparation. So that is like in a way similar, yeah, like you have all the data but it needs to be prepared in a certain way to be ingested in or to train models. So you could see some parallels here, like how to map from one domain to another. uh, and also because the programming model nowadays is so low level with so you program at qubit and gate level. So it is like in the classical world, this is the time of ENIAC. Yeah, so this is 1950s where you have like cathodic lamps which are like qubits. So they kind of behave how you want it. Yeah, like but they need to be tuned. And then you have like wires that are plugged, and those are the gates. Yeah, so that's the level. So but if you look at also like from machine learning, they so you have uh, some basic algorithms or basic techniques, but as a developer, you work with higher level concepts. So there are intermediate libraries like Keras, TensorFlow, PyTorch. Yeah, so you are not, unless you want to develop a new algorithm, you are not exposed to the mathematics or to the deep mathematics. Yeah, and you are more into like applying this. Yeah, we don't have that yet in quantum computing. So
Okay. I want to touch base on the maturity of the software stack that you mentioned. I think you were talking about the different libraries and frameworks that today are mainstream from the large providers like Google, Microsoft, and IBM. When I start thinking about it, I compare this, and that might be a very loose comparison, so apologies if it does not hit home. Like a lot of programmers, I think back in late 90s when I started programming, or early or mid 90s when I started programming, was about programming a single computer. And obviously, the web paradigm came, and you start thinking about, oh, what does it mean by building a network program that runs on networks, so client server paradigm. And then we went into this whole distributed systems. So the map reduce paradigm, right? Oh, how do you build a system where you have data sharded across multiple machines and computing needs to, or logic needs to then spread around. And when I start looking at these waves, I think a lot of these benefits around client server architecture or building MapReduce based programs helped me to not have to worry about how what does it mean by moving data from one machine to the logic to one machine. The abstraction was super good, and I could build really complicated systems around that. How do you see that being traveled to the quantum space? Like, if I am not a physicist and maybe I know basics of quantum computing, what is the maturity of frameworks tooling that today is available so I can get into it without worrying about maybe the physics of superposition, physics of transformation and entanglement, for example?
yeah, well, I think that that's a very good question, and like abstractions. So that's like you build more complicated or more like yeah complicated complex, let's say complex, not complicated. So more complex things by having the right abstractions. Yeah, and if you look at the quantum world from outside, the quantum computer, you could see the quantum computer as an accelerator. So this is like a very fast accelerator, so matrix computation, like matrix solver. Yeah, and we kind of have a similar thing with the GPUs. So the GPUs have similar, like at the hardware level, you have pipelines and this kind of cores, but you don't work with them directly as a programmer. So you have abstraction layers. I think that CUDA is the prime compute, this kind of computational infrastructure that allows you to use the GPUs. But on top of that, there is the MPI that is used in the supercomputers that allow you to abstract or to partition the program or a bigger problem to smaller parts and distribute it. And I think that these kind of metaphors will ultimately translate into the quantum world. We don't know at this stage like how. So current quantum computers are tiny, yeah, in terms of qubit numbers, and you see announcements every week that some company has increased the number of qubits and so on, but they are still small. So yeah, I think that the IBM said that announced that they are working on a 1,000 nodes, 1,000 qubits system. Some other companies, I don't remember now which one, it was like a couple of weeks ago, it was like 250, and they start to talk about logical qubits, so they have built-in error correction, but they are very tiny, yeah? And there is a problem of like with the miniaturization, because you cannot make these things very small, because the technology to build them cannot be reduced. Like, for example, if you take the superconducting, which are like the most successful implementations nowadays, so they require temperatures close to 0 Kelvin, yeah, which are hard to get. So you need a cryogenic chamber, and how many things can go there, because you need also the communication with the qubit. So some sort of clustering, packaging of this like quantum classic system. So we will see that kind of thing coming up. I think that a recent development, so photonic qubits, but those are like a special breed of applications. But also the semiconductor spin electrons. So this is using technology, like manufacturing technology that is used in traditional chip manufacturing. So it has some potential for scaling. So packing more qubits into a smaller die, and then you will get it. But at some point, these ones, they need to be packaged into larger, and we live currently in the what is called the NISQ quantum era. So this is like noisy intermediate scale quantum. Yeah. So small number of qubits with high errors. So you cannot do too much about it. But in few years we will move into quantum error correction is a hot topic now. So how to bring together, or how to use several qubits to achieve a more like accurate qubit, and that qubit is called logical. And already at that level, so the logical qubit is an abstraction. Yeah, like it brings us, so it takes you away from from the hardware implementation, because it kind of hides it already at that level, even if it is like we are close to the metal. Yeah. And from there, I don't know, like this is also a hot area. Like, how do you program this? What kind of programming languages beyond gate level? So something that is like, what will be, so it's kind of ironic that in quantum computing we use Python to program what is called the quantum assembly. Yeah, so a very high level classical language that has garbage collection, dynamic types, and all these things. We use that one to program assembly. So I'm wondering, like, what would be like a native quantum Python, how that will look like, or what kind of libraries we can use to program like masses of qubits. And at that point you will see probably like so in a way, like we are, so on the quantum side we are lucky to have like 70 years of experience of software engineering from the classical side, and all the lessons, the good lessons and the bad lessons, they need to be how is like digested in the quantum computing space. But yeah, this is like in the lower levels of the stack. But if you look higher up, well, there are simulators that allow you to simulate quantum hardware. So all like Qiskit has air, Penny Lane has Lightning. They are using, so you could run programs that are using GPUs. So CUDA, so they are using MPI. So for supercomputing or clusters of GPUs, fast interconnects between them, so merge them, get more memory. And yeah, that's like, I think that because the programmers are, so the tools that the programmers are using are so far away from the actual hardware that so I don't like where will be the equilibrium? Yeah, like the from the software stack, the abstractions will go deeper. Yeah, and the hardware people will optimize their hardware, and they will come with some other abstractions, and where do they will meet at some point. Yeah, but how does one that one looks is kind of a open question. Like, I mean, if you go 10 years back in classical computing, or if you travel from that day to today, you would be like, this is like science fiction. It doesn't exist yet.
Thank you so much, Vlad, for covering that. I want to maybe cover some areas which may be very early stage and we're developing, especially with the rise of generative AI, a lot of machine learning application, large language models. Two things are often said in that space is one, improving the speed of training and using large models that can obviously be trained on large corpus of data and then use that to really build smaller, more modular models. And the other problem that they are looking at is improving inference speed, right? So a very laymanish example is you go to chat GPTs or the llamas and you have an inference time. And obviously you can apply something like quantization to really reduce a large model to a smaller kind of palatable system. I'm trying to understand, how do you see that problems around training large models and also improving inference around using these large models connected to perhaps the benefits that quantum computing offers? Like, do you see even any connection with that? Like, if I have to put it more explicitly, can I actually today, or maybe in the few years, take a quantum computer and say, oh, I can actually train even larger models with a large amount of data and reduce the training time to very small time thanks to a quantum computer. Is that even a possibility, or we're talking about two different things?
Uh, so my understanding of LLMs is, let's say, medium. Yeah, like I, I'm I aware of some building blocks there, like and patterns of building these applications. I have, let's say, prototype or read about them and follow what they do. I cannot say exactly because they are quite complex machinery. So is not only one. Maybe we run it as one command, but to train them is not as simple. What I can say from quantum machine learning is that, because there is this field also, like uh, I I think that so parts of the training are let's say prone to be accelerated, and this is because uh, I think that also in the like machine learning, deep learning, you have this kind of problems where let's say that, so nowadays you make some guesses, yeah, because you cannot explore all the possibilities. So it is like so probably it is an optimization problem in the end, or it can be thought into that way. So yeah, like the answer will be like some bits inside that will definitely be optimized, or like the improve. You will see improvements with quantum technology. I think that they will be because in quantum there is no, you cannot think in terms of like this kind of flow control that we have, or conditional logic that we have in classical. So that part will not be like, for I don't know when that will come. Maybe there will be something like I read about quantum decision making, a paper now, but is like very experimental. So one colleague uh, pointed to that area. Uh, Definitely there will be some parts that, but this is, and I think that the if you look at penny lane, so this is a framework that you can do general purpose computing, but you can do also machine learning, and I think that that is the primary use case of it. Their approach is, you have a classical, so the program, you write one program, and this is a Python, and then they use some directives for parts of it. Those will be implemented as quantum components. And when you run it, so if you have the proper runtime, you will get like the compiler is smart, and it will know that, okay, this part is classic, this part is quantum. So the way I see this is like, I explained like what, so this problem that is like native to quantum computing. So if you understand the problem, you will get a good result. Yeah, like you are able to map to qubits. So it will be like a gradual approach, like a gradual adoption. So in some parts will so quantum computing will lurk into this data like data center infrastructure, and it will be used to accelerate specific parts in the beginning. We are not yet there, so everything is experimental at this time, or is for learning, but they will appear there. Your master some area, then it will be transferred to another area, into another area. So we will have, so maybe you will not see it like that quantum computing is used there, but probably it will be like the stock price of quantum computing manufacturers will skyrocket in the same way as, so you will see like you could observe that the adoption is indirectly observed like the same way we see the GPUs nowadays. Yeah, like you sell more. So definitely there is demand. So that's like how
we're not using this to give people advice to buy stocks.
No, definitely no, because it's so far in the future. It's just an analogy, like and the way to observe like when things will change, maybe.
That's a very good example, especially like using the popular example of Nvidia, right? So its stock has massively increased because it saw these applications coming up in the future and they started preparing it really long ago. And I think the use cases started coming in, really kind of catapulting this particular brand into different space. I think we are at the tail end of our conversation, and I think we started talking about the future of this. And one phrase that often comes in media and popular kind of parlance is the topic about quantum supremacy, right? Brands are talking about it, Google is talking about it, or IBM is talking about it. What is your understanding of this whole phrase called quantum supremacy and quantum advantage that companies are talking about?
Yes, so this is a good question. So I thought that so 1 year ago I thought that quantum computing is about supremacy, and this was in a way, so it was not only my impression, but this is somehow for a larger audience, not the quantum educated. This is because Shor has this amazing results, like comparing to traditional. But over time, I think that the proper term to use is advantage. And this would be like, by advantage is like it gives you better than traditional. And this is something that we start to move from something that is like a kind of absolute like supremacy to something that is like an engineering term or something that is you can work with. So you are not like chasing some unicorns or whatever, but you could see hands-on like for your problem if quantum technology gives you advantage. And we understand by quantum advantage that it performs better than classic equivalents, and that would be the tipping point of quantum adoption.
Amazing. Vlad, thank you so much for giving a kind of a high level view of the entire domain. I love to obviously go into details of this, but we will be here forever.
Yes.
If people who are curious and want to learn more and also reach out to you, what is the best way for them to connect with you? What is your thoughts on that?
Yeah, so I'm trying to keep some presence online. So this is I'm posting from time to time on LinkedIn. So searching for my name is like the way to do it. So probably we will have some kind of overlay at the end, like with some disinformation. I have a blog, so vladštirbu.com. So that's the easy, not as many posts as I wanted, and then experiments go to my GitHub, and also I think that I'm also like easy reachable for questions and discussions with my email address at university, and which will be also like available there. So I try to answer as fast as possible. So sometimes I'm traveling or attending a conference, but if you have any questions about this, then shoot. And because I'm an academic these days, so what we produce is papers or research papers. Mine we try to publish them with open access, so they can be downloaded and accessed from the publisher's website whenever is possible. Otherwise, on Archive, this is there, and you could see more, or you could read more about what we are doing at University of Jyväskylä in this area.
Amazing. The last point and the last question for you: if somebody who is interested in this and is not getting the chance to do this accidental involvement like you, what can they do to break in? What they can do to get started? What is your advice to them?
Well, starting is rather easy. So it does not. So you can do it on your own computer. So most quantum development kits are open source and are available from either. So you do a pip install and that's it. So Qiskit is there, PennyLane is there, Circ is there. So it does not require too much to get starting and to work. These tools are very well integrated with Jupyter notebooks. So if you are into experimentation and documenting at the same time what you do, so probably the notebook metaphor is the right one for you. If you are more serious and you want to package your code and do some advanced Python, not everything is in one file, then Visual Studio Code or any IDE is probably the way to do it. All these toolkits, they are coming with their own simulator that runs at least on the CPU. So circuits of like 20 qubits, maybe you can run on any computer. So even on like ultra portable, like a MacBook Air, it works. For larger circuits, you need something that is probably not available in the normal computers that we use. So some modern NVIDIA or AMD GPUs. So they are so both CUDA and ROCm compatible accelerators are supported by the quantum simulators. And if you want to go higher, then you need to find a commercial entity that is serious into this, and they have something so that you can run in the cloud, or some research institute so that you can have access to supercomputers. But that's the way to, like, from the hello world to the deep end. Yeah, but the hello world is very simple. So I encourage everyone to give it a shot. I think that most providers, they have very good documentation, especially I think maybe the gold standard is PennyLane and IBM Quantum. They explain both, so they can go, or you can go deeper into the mathematics too if you want. So they have links to more in-depth concepts there on their own site, but they have also links to research papers, because this is still a highly scientific domain, and luckily it is rather open, so you have access to a lot of information, so publications, source code, and yeah, I think this would be also something that can turn around some careers, like for people that look for something exciting and they want to try something new.
Amazing. I really want to thank you, Vlad. It was such a pleasure to have you on the podcast, talk about your journey, but also your passion project, your field of area. And I really hope we can actually connect again and actually explore this whole domain in more details, maybe speculate a bit. And who knows, we can see more demos and, try out stuff. That might be another way to, dig our hands and explore this area. So again, thank you so much for
You are
coming
welcome.
over and also giving the audience a chance to learn about you.
Thank you. Thank you for the opportunity.